According to quantum mechanics, light is a wave, but it can be emitted or absorbed only in discrete chunks. No matter how continuous and homogeneous might look a wave of light, when we detect it, we detect only a discrete chunk or a quantum at a time. This chunk is called photon. Not only light, but any kind of matter or field behaves in this dual manner. A beam splitter is a half-silver mirror. It reflects only half of a wave of light and it transmits the other half. If we place a detector to count the reflected photons and another one to count the transmitted ones, we can see that any photon is either reflected or transmitted. Therefore, the beam splitter can't split the photons. But if we collect the two halves of a beam sent through a beam splitter by using mirrors and recombine them using another beam splitter, we recover the original beam. Only one of the detectors will detect photons because now the beam is no longer split. But we should expect that half of the photons are reflected and half of them are transmitted. So we expect that half of the times one detector clicks and the other half the other detector clicks. The fact that when we recombine the beam we don't see this means that each of the photons travel both ways before being recombined. We arrived at a paradox. If we recombine the beam, it turned out that each photon traveled both ways, but if we don't recombine it, it turned out that each photon took either one path or the other. It seems that when the photon encounters the first beam splitter, it is either reflected or transmitted, in case it will not be recombined in the future, and it is split if it will eventually be recombined. But how can the photon know its final fate from the beginning? Especially since, as Wheeler pointed out, we can delay the decision whether to recombine it or not until after it leaves the beam splitter. Why never happens that we decide to recombine a photon that it is not split? This is the central mystery of quantum mechanics. The standard interpretation is that after leaving the beam splitter, the photon travels both ways, but if it turns out that it is not recombined, it chooses one path or the other and sticks with it as if that was its path from the very beginning. It simply forgets about the other path. In the many worlds interpretation, it travels both ways, and if it is not recombined, the universe splits in one universe in which the photon was reflected and another universe in which it was transmitted. There are many other interpretations, each of them trading some mystery for another. One way to interpret this paradox is the following. Imagine three pictures, one in which the photon was reflected, one in which it was transmitted, and one in which it travels both ways. Cut each of the three pictures and turn it into a jigsaw puzzle. There are three pieces showing what happened when the photon encounters the first beam splitter, three pieces showing what happens when it encounters a mirror, and the other three for the other, three pieces showing what happens when it is detected. Each of the pieces is a snapshot of a part of the world, and there is no paradox yet. As observers embedded in the world, we only have access to a local region around us. We explore the world by collecting pieces of the puzzle and combining them with what we already have. We only receive pieces that fit consistently with the ones we collected so far. This is the global consistency principle. At any time, there is always a self-consistent global solution fitting all the local pieces we collected. The consistency should be maintained even between pieces of the puzzle collected at a large distance. The spin of an electron can be visualized as an arrow pointing in a direction in space. In a magnetic field, the spin can be oriented either parallel or anti-parallel with the field with some probabilities. These probabilities depend on its previous orientation. It is more probable that the resulting orientation is the one making the smaller angle with the previous orientation of the spin. Therefore, the orientation of the spin is correlated with its previous orientation. If two electrons whose total spin is zero are separated and placed in two magnetic fields, their spin orientations are correlated in the same way as the successive spin orientations of a single electron. This means that the spin orientation of one of the two electrons depends on the direction of the magnetic field chosen for the other electron. This version of the Einstein-Podolsky-Rosen experiment shows that the spin orientation of an electron has to be consistent with the choice made for the other electron, no matter how distant they are now. But why is this so? The key to understand this is to borrow from relativity the timeless view. Relativity provides a picture of a world in which space and time are combined in space-time, a four-dimensional block. The flow of time is only an illusion we experience. This is similar to a movie on a DVD. an immutable block containing characters that take part into actions which are illusions and only become apparent when we play the movie. Quantum mechanics, on the other hand, is governed by evolution equations, which suggest that time flows and things happen. But relativity can also be formulated as a time evolution theory. We expect that quantum mechanics can also be formulated as a timeless theory. If we do this, then the idea that the solutions should be globally consistent in space and time becomes more natural. Hence, the paradoxes of quantum mechanics appear only as being caused by the illusion that time flows, and we can choose to combine incompatible pieces of the puzzle. The main objection people have against this idea that time is an illusion is that it contradicts our direct experience that time flows. They also worry that this would violate our freedom to choose. Well, I think that time still can flow and we can still be free to choose, even if we admit this block worldview, which is very useful for that matter. The idea is that what we choose now is free as long as it doesn't contradict the puzzle pieces we already collected. Remember the 3 sets of jigsaw puzzle games. Say that we have 3 of the 4 pieces, but we haven't turned them up yet. Now say we choose the 4th piece, representing whether the photon is recombined or not. The global consistency principle forces the other pieces to be compatible with our choice of the 4th piece. So, if we choose to recombine the photon, when we turn up the other pieces, we see that it traveled both ways. If we choose not to recombine it, when we turn up the other pieces, we see that it was either reflected or transmitted. Our freedom goes only this far because we can choose between the photon being reflected and transmitted. But what if we look at the first piece first and we see what happened with the photon at the first beam splitter? Could we then see that the photon was reflected and still choose to recombine it? To see what happens with the photon immediately after it leaves the beam splitter, we have to put detectors there, and this means that we choose not to recombine it. This shows that there is no contradiction between global consistency and freedom of choice. The key ingredient is that we can only make choices that are consistent with the pieces of the puzzle which are already collected.